Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group lecture number 57, in which I will solve some problems on factorization theorem and fundamental theorem of homomorphism or first isomorphism theorem. Now we solve a problem. Problem is, let G be a cyclic group of order 10 and G prime is a cyclic group of order 5, so that there exists a homomorphism phi of G onto G prime with order of kernel of phi equal to 2. Now we solve this. Given that G be a cyclic group of order 10, let A be the generator of this group, therefore G is written as G is generated by A and order of G equal to 10. Let G contains elements A square, A cube, A to the power 10. Again, also given that G prime is a cyclic group of order 5. Let B be the generator of this group. Therefore, G prime is written as G prime is generated by B and order of G prime equal to 5. Let this is number 1, this is number 2, this is number 3. Let G prime equal to B square, B cube, B to the power 4, B to the power 5 equal to identity element of G prime. Here also A to the power 10 equal to identity element of group G. Let this is number 4. Let H is a set containing elements A to the power 5 and A to the power 10 equal to identity element of group G. This is number 5. It is clear that H is a cyclic subgroup of group G generated by A to the power 5. Therefore, H is written as cyclic group generated by A to the power 5. Since H is a subgroup of the cyclic group G, therefore H is a normal subgroup of G. H is a normal subgroup means the quotient group, therefore quotient group G by H exists. Order of G by H equal to order of G by order of H. Order of G is 10 and order of H means number of elements in H is 2, that is 5. Let this is number 6 and this is number 7. We may write G by H quotient group as AH, A square H, A cube H, A to the power 4 H and A to the power 5 H. And this is equal to H. Let this is number 8. Number of elements in quotient group G by H is 5 and 5 is a prime number. Therefore, G by H is a cyclic group which is generated by AH. Therefore, G by H quotient group equal to a cyclic group generated by AH. Let this is number 9. Let theta is a mapping defined on G into G by H such that theta A to the power R equal to A to the power R H. Here this is G, this is G by H and theta be a mapping defined on G into G by H quotient group. Here for A to the power R we get an image A to the power R H. Since theta A to the power R multiply A to the power S equal to theta A to the power R plus S equal to A to the power R plus S H equal to A to the power R A to the power S H equal to A to the power R H A to the power S H. Since H is a normal subgroup, and a to the power RH equal to theta a to the power r, and a to the power sh equal to theta a to the power s. This is number 10. Therefore, theta is a homomorphism for any a to the power r h belongs to g by h. There exists a to the power r belongs to g such that theta a to the power r equal to a to the power r h. Therefore, theta is onto. This is number 11. From 10 and 11, we get theta defined on g into g by h is onto homomorphism. Here h be the identity element of g by h. Since h be the identity element of quotient group g by h. Now, kernel of theta equal to a to the power r belongs to g such that theta a to the power r equal to identity element h equal to a to the power r belongs to g such that theta a to the power r means a to the power r h equal to h. This means a to the power r be the all elements of h. This equal to h. This is number 12 and this is number 13. From 12 and 13, we get theta is a natural homomorphism with kernel of theta equal to h. This is number 14. Since g by h and g prime both are cyclic groups with same order 5. Therefore, G by H quotient group is isomorphic to G prime. Therefore, psi is a mapping defined on G by H to G prime is isomorphism. This is number 15. This is G by H quotient group and this is G prime, and psi be isomorphic mapping defined on quotient group G by H into G prime. The isomorphic mapping psi is defined as psi a to the power r h, its image is b to the power r. Let this is number 16. Therefore, by factorization theorem, there exists an onto homomorphism phi defined on G into G prime such that psi theta equal to phi. Now, phi a to the power r equal to psi theta a to the power r. This equal to psi theta a to the power r. This equal to psi a to the power r h. Theta a to the power r equal to a to the power r h, and psi a to the power r h equal to b to the power r. Let this is number 17 and this is number 18. Here image of a to the power r is b to the power r. Also, by factorization theorem, car phi equal to car theta and car theta equal to h in 14. Therefore, order of car phi equal to order of h equal to 2. Proved. Now we solve the next problem. Next problem is, let G be a group of real numbers with binary operation addition and H be the group of integers with binary operation addition and G prime be the group of all those complex numbers xi such that modulus of xi equal to 1, and this is a group with binary operation multiplication. Prove that the quotient group G by H is isomorphic to G prime. Now we solve this. Since R be the set of real numbers, Z be the set of integers, and C be the set of complex numbers. Let phi be a mapping defined on G into G prime defined by phi x equal to cos 2 pi x plus I sin 2 pi x. Here we have G is R with binary operation plus and G prime, and G prime contains all those complex numbers whose modulus is 1, and this G prime with binary operation multiplication, and phi be the mapping. For element x belongs to G, we have here cos 2 pi x plus I sin 2 pi x. Since modulus of cos 2 pi x plus I sin 2 pi x equal to cos square 2 pi x plus sin square 2 pi x. This is equal to 1. This is number 1 equation. Now let x, y belong to G. Therefore, phi x equal to cos 2 pi x plus I sin 2 pi x, and phi y equal to cos 2 pi y plus I sin 2 pi y. Phi x plus y equal to cos 2 pi x plus y plus I sin 2 pi x plus y. This is number 2, this is number 3, and this is number 4. Since G prime is a group with binary operation multiplication, so this is phi x, phi y belong to G prime, and we take operation phi x multiply phi y. This equal to cos 2 pi x plus I sin 2 pi x multiply cos 2 pi y plus I sin 2 pi y. This equal to cos 2 pi x multiply cos 2 pi y plus I sin 2 pi y multiply cos 2 pi x plus I cos 2 pi y multiply sin 2 pi x minus I square, means minus sin 2 pi x sin 2 pi y. This is equal to cos 2 pi x multiply cos 2 pi y minus sin 2 pi x sin 2 pi y. This is cos 2 pi x plus 2 pi y plus, we take common here, I sin 2 pi, here sin 2 pi x cos 2 pi y plus cos 2 pi x sin 2 pi y. This equal to cos 2 pi x plus y plus I sin 2 pi x plus 2 pi y. This equal to cos 2 pi x plus y plus I sin 2 pi x plus y. This is number 5. From 4 and 5 we get right side same, therefore left side be same. Phi x plus y equal to phi x multiply phi y. This is number 6. Therefore phi is a homomorphism. This is number 7. For any xi equal to cos x plus I sin x belongs to G prime, there exists x by 2 pi belongs to G such that phi x by 2 pi equal to cos 2 pi multiply x by 2 pi plus I sin 2 pi multiply x by 2 pi equal to cos x plus I sin x. Therefore phi is onto mapping. Onto mapping means homomorphism. Onto homomorphism. This is number 8. Since h equal to set of integers with binary operation addition is a normal subgroup of G, which is equal to set of real numbers with binary operation addition, because left coset of Z equal to right coset of Z with respect to binary operation addition. Therefore quotient group G by H exists. The identity element of quotient group G by H is H. This is number 9. Now kernel of phi equal to all those elements of G such that phi x equal to identity element of G prime. Since identity element of G prime is 1 be the identity element of G prime equal to x belongs to G such that phi x is cos 2 pi x plus I sin 2 pi x equal to 1. This is possible only when x belongs to Z. That means this is equal to Z equal to H equal to identity element of G by H. This is number 10. Here we have G by H. Therefore, phi defined on G into G prime is onto homomorphism with kernel of phi equal to H. This is number 11. Therefore, from fundamental theorem of homomorphism or first isomorphism theorem, there exists psi defined on G by H into G prime is an isomorphism, implies that G by H means car phi is isomorphic to G prime. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.